Welcome to the debate. What if a web server could, mathematically prove that it is physically impossible for it to run any faster?
It sounds like a theoretical physics problem, honestly.
Right, it totally does. But today we are looking at x-gnosis. It's a web server built on the Aeon stack that claims to be the first provably optimal server. And it doesn't rely on tweaking and guessing, but on, theorem server optimality.
Yeah, which is an actual mathematical theorem composed of, 14 mechanized theorems?
Exactly, 14 of them, verified in TLA+ and Lean 4. So it frames a really fascinating disagreement for us today. Does achieving mathematically proven optimality at the server layer fundamentally revolutionize real-world network performance? Or do the chaotic physical realities of network transport and, legacy client protocols render these theoretical guarantees less impactful in practice?
That is the core of it, yeah.
So to state our positions briefly, I believe x-gnosis' formal verification and that resulting 7.6 million requests per second benchmark represents an undeniable paradigm shift in server architecture.
And I argue that formal mathematical optimality on the server, while beautiful, ultimately fails to overcome the physical bottlenecks of hostile networks and legacy client constraints.
Fair enough. Well, let me start off by saying if you are a developer used to tweaking Nginx or Apache, this is a completely alien way of thinking about a server.
Oh, absolutely.
Right? I mean, normally you tune empirically. You adjust a buffer here, you expand a thread pool over there, and you just sort of hope the benchmark goes up. But x-gnosis uses what they call a zero-deficit fork, race, and fold schedule.
Which is quite a mouthful.
It is, yeah. But instead of guessing, the architecture proves by definitional equality in Lean actually that it achieves the critical path make-span and Pareto optimal resource usage, meaning literally no other configuration could use fewer resources.
Right.
So when you see that 7.6 million requests per second single-thread pipeline benchmark, it's not some highly tuned fluke. It is the inevitable empirical realization of the proven bound.
Well, I come at it from a different way. I mean, I have profound respect for the elegance of those proofs. I really do. But the math relies on a DAG, a directed acyclic graph. Think of it as a perfect mathematical map of tasks, right? But that map is completely isolated from physical reality.
I mean, isolated is a strong word, but go on.
We'll look at the live shoot-off results from March 17th. When they tested x-gnosis against a standard Nginx server under lossy or, hostile cellular networks, they converged to virtually identical transport ceilings.
Sure, the cellular tests.
Right. They both bottlenecked around 5 to 6 requests per second in hostile conditions. So the physical wire, not the server's internal math, remains the true dictator of performance. The math inside the box is perfect, but the wire outside is not.
I get that. But that tension between the perfect blueprint and the messy real world, that's exactly where we need to look at x-gnosis' resolve layer.
Okay, let's talk about the resolve layer.
Let's examine what happens when a simple static file request comes in. The server doesn't check the memory cache, wait to see if that fails, and then check the disk. No, it simultaneously races 3 resolution strategies.
Right, it does the in-memory LRU cache memory mapped file access, the mmap, and a direct file system read.
Exactly, all at once.
Wait, it fires all 3 requests at the exact same time?
Yes.
Doesn't that waste massive amounts of CPU? I mean, if you're constantly triggering file system reads you don't even end up using?
Well, it would, if it didn't have a mechanism called venting. It's essentially a true first success race. It's like ordering the exact same package via FedEx, UPS, and USPS at the exact same time.
Okay.
The millisecond the FedEx guy hands it to you, the other 2 delivery trucks magically vanish from existence.
Magically vanish. Right.
Well, mathematically vanish. That venting is proven by a theorem called THM server race elimination. It guarantees there is no cross-path blocking whatsoever. It's like engineering an engine with 0 internal friction. Even if the road is bumpy, the engine itself never wastes a single drop of fuel.
Okay, that's a compelling argument, but have you considered the vehicle you are forcing that perfectly frictionless engine to actually drive?
What do you mean?
Let's look at the micro front-end site shoot-off data. Yes, x-gnosis dramatically reduces framing overhead down to 19.4% compared to Nginx's 31%. That's great.
It's incredible, yeah.
But how does the data actually reach the user? The browser is still speaking HTTP 1.1.
Ah, sure.
Yeah, that legacy protocol still requires 11 sequential round trips sending messages back and forth just to load the resources. So the internal engine might be frictionless, sure, but the server's still forced to navigate a fragmented, highly inefficient road dictated by standard browsers.
Well, I see why you think that. But let me give you a different perspective. You are treating HTTP 1.1 as this immovable constraint.
Because for most users, it is.
Right. But x-gnosis anticipates exactly this problem because it is a dual protocol server. For flow-aware clients, it uses Eon Flow.
Yeah, the Layer 4 protocol.
Exactly. It provides the exact Layer 4 protocol to bypass those legacy browsers entirely. Instead of sending bulky HTTP headers with every single request, Eon Flow uses tiny 10-byte self-describing frames with 0 per request headers.
Right.
It drops the framing overhead to a staggering 0.03%. When you switch that same micro front-end site to Eon Flow, those round trips drop from 11 down to exactly 1.
Wow.
Yeah. And the THM protocol deficit theorem backs that up. It guarantees that the pipeline introduces 0 mathematical overhead.
Look, I'm sorry, but I just don't buy that as a practical solution.
Why not?
Let me tell you why. You are describing a beautiful, frictionless highway that basically no one currently drives on. We have to look at adoption reality here.
Okay, sure, adoption takes time.
But to handle normal web traffic today, x-gnosis includes this massive compatibility shell called Gnosis Ditto.
Yes, for Express, Flask, Spring, all of those.
Right. And if a developer has to maintain that immense compatibility shell and fall back to the traditional blocking path, which, by the way, only gets around 153.8K requests per second on macOS for plain text, then Eon Flow is just an edge case luxury. It's not the standard operating reality.
That's an interesting point, though I would definitely frame it differently.
How so?
That compatibility shell is a bridge to the future, and it actually highlights how powerful the underlying abstraction is. Think about how x-gnosis handles a standard nginx.conf file.
Okay.
Instead of just reading the configuration line by line during runtime, it dynamically translates those instructions into a .gg topology program.
Right. The semantic families.
Yes, it turns your config into a mathematical map so it can calculate the absolute fastest route for data. And that formal math scales so seamlessly that it runs an optional D1 back to VFS layer and even includes a native high-frequency trading parallel simulator,
The HFT simulator, yeah.
which evaluates 32 million tick config evaluations in 1.5 seconds. That proves the abstraction works at massive edge deployment scales.
But that abstraction introduces its own logical friction. You are taking a massive, messy, legacy application and transcribing it into a topological pipeline.
And verifying it.
The math strictly verifies the runtime execution schedule, yes, I'll grant you that. But it cannot verify the semantic fidelity of the developer's original intent once it passes through that translation shell.
I don't think...
You might be executing a fundamentally flawed application with perfect mathematical efficiency.
I'm not convinced by that line of reasoning because the invariants, the core rules of the system, are explicitly preserved at the protocol as execution layer.
But there's still translation risk.
Sure, but stepping back, my view is that x-gnosis, by composing Layer 2 formal languages and Layer 3 distributed computation into a Layer 7 server architecture, it fundamentally proves that mathematical verification is the future of systems engineering.
And while I absolutely agree that the zero-deficit internal scheduling is a massive breakthrough, I really do theoretical optimization certificates stop at the network boundary.
They do stop at the wire, yes.
Real-world performance is always going to be vulnerable to uncontrollable variables, like the physical wire and legacy clients.
I hear you. Though we do find a strong point of convergence on how x-gnosis handles Layer 8 laminar transport.
Oh, absolutely. The per-chunk codec racing.
Yes. Instead of waiting to read a whole file before compressing it, it pipelines compression directly with the disk I/O.
It actively compresses data chunks as they stream right off the disk. That mechanism strictly dominates traditional send file approaches. It's just a massive leap forward for delivering compressible content.
Precisely. And there is much more to explore here, particularly how their new Tauri Edge runtime lanes and local first host integrations might start executing server code directly on the user's local device.
Which further blurs the line between client and server.
It really does. It leaves us to wonder if the boundary between the perfect mathematical blueprint and the physical world continues to dissolve. Is mathematical optimality the ultimate destination or just one piece of an entirely new puzzle?